I've taken my first steps in Rust on the Pico 2 and I liked what I saw. Through that video I started a conversation with Jonathan Pallant, one of the leaders in the RPRS HAL. He kindly offered some time for a fireside chat about Rust. Hi, I'm John, your concierge to the world of the Raspberry Pi Pico, Pico 2, robotics, IoT and other fun tech. Remember to subscribe and join the community. This video is sponsored by WolfSSL. WolfSSL provide both open source and commercial supported libraries for security that I use all the time in my embedded systems. But did you know also that WolfSSL actually supports Rust, and we can actually use those cipher suites in the Rust language too as a provider, both using software algorithms and hardware acceleration, which is great when you're playing with Rust. So go check out WolfSSL today. So I'm delighted to be joined by Jonathan Pallant, leader, developer and trainer in Rust, the programming language. Hi, Jonathan. Thank you very much for joining me on the show today.
Oh, my absolute pleasure. Great to be here.
For those of my audience who haven't come across you, or certainly behind the world of Rust in the Pico space, can you give us a bit of an intro to who you are?
Sure. So yeah, my name is Jonathan Pallant. I'm a full-time Rust trainer and developer at FreeRTOS Systems. One of the things we produce is a qualified Rust toolchain. So that then allows people to use Rust for safety critical systems, automotive, industrial, medical, that kind of thing. So when I'm not working on that toolchain, I teach Rust professionally. So running training courses for people, we tend to do those over Zoom. And then I have a lot of, embedded hobbies, which I do in Rust. So yeah, sometimes it feels like Rust all day long.
Excellent, good stuff. So I came to hear about you when you popped up as an author for the RP2350's HAL after my review on Rust on the channel, looking at it from the Pico 2. How long have you been in this Rust world? I know that you were on the Rust Leadership Council, so I presume you've got all of the grey hairs from this.
Yeah, it's been quite the wild ride. So I think 2017. So not at Rust 1.0, but a few releases in, I was introduced to the language by a colleague, and I've been an embedded C developer for a long time. Gosh, I mean, I've been programming professionally for at least 20 years at this point. So yeah, I'd done a lot of work in C, and I'd always written the desktop tooling in Python because nobody wants to write, cross-platform log analyzers in C. That's horrible. And so when Rust came along, I thought this is incredible, really, because this solves a lot of the problems I have as an embedded C developer. I don't have to use Python for the desktop bits. I can use the same language. We've got much stronger typing. We've got these enums that allow me to sort of keep my data separate, and I'm not confusing things like I might do in C. So I really like the language. I started to learn it. And for embedded development, it was really early days back in 2017, 2018. You couldn't compile Rust for a microcontroller on the stable compiler. You had to use Nightly. You had to opt into all of these optional features. So around 2018, I helped co-found the Rust Embedded Devices Working Group. There were a bunch of us kind of experimenting with the state of the art in Rust on microcontrollers. We got together and we said, well, we need to kind of build some abstraction layers and build some standardization so that people can come and use Rust on microcontrollers. We think it's a good idea. We'd like more people to do it, but we're going to need to put some things in place that we're going to get some compiler changes made so that can happen. The Embedded Devices Working Group is still going. They're having a lot of successes. I spent about 6 years on that group, volunteering my time. And yeah, kind of late 2018, we started to get Rust working on microcontrollers, specifically ARM Cortex-M microcontrollers. Some of the most popular ones, certainly some of the easiest to program. And that's all working on the stable compiler and has been ever since. I joined the Rust Leadership Council about 18 months ago. I was elected as a representative. So basically that council has representatives from each of the major teams within the Rust project. and they sort of nominate someone. And I did about a year with the council, kind of sort of overseeing the Rust project to give me really good insight into how the project itself works. And then, yeah, the RP2040 thing was kind of interesting. As if I don't have enough to do, at one point I was the town mayor of St Ives, where I live. So I was on the town council, local government, and the town councillors pick someone to be mayor every year, and I drew the short straw, and I was the mayor of St Ives, and it was during COVID. So yeah, we didn't really get to do a lot of like charity balls or Christmas dinners or cutting ribbons, kissing babies, any of that kind of stuff. It was a very different time. So a lot of meetings on Zoom, and I wanted to make some money for charity. I thought, well, I can't do events. And then the RP2040 appeared, just sort of out of nowhere. I thought, well, this is fascinating. Dual M0 plus cores. Seems like they've designed a bunch of peripherals themselves. I wonder if I can run Rust on that. I've been running Rust on lots of other ARM microcontrollers. It's kind of a fun thing to do. Say, here's a new chip. How can we get Rust going? So I did a charity live stream. I made a few £100, and within about 5 hours from never looking at the chip, never opening the datasheet to, we had a blinking LED running in Rust. I thought, well, yeah, okay, this seems to be relatively well documented. It kind of makes sense. The bootloader situation is weird. And so that was that. I sort of published what I'd done and said, yeah, this looks interesting. This was a couple of days after the 2040 launched. And then, yeah, a couple of groups formed. So I hang out with the RPRS group, and yeah, they've kind of looked at that very basic starting point I had, and now there's this sort of wonderful, vibrant ecosystem around, yeah, Rust on Raspberry Pi Silicon.
Excellent. And then, we got to that wonderful place where the RP2350 actually had Rust support day one.
Yeah, that was
exciting.
Yeah, that was a great opportunity. So I'm very fortunate to live in Cambridge and go to events in Cambridge, and got to know people from Raspberry Pi and talk to them about Rust. And as someone who sort of wants Rust to succeed professionally, it's always in my interest to get support from silicon vendors. I think it's fair to say that there are only a handful of silicon vendors who are really investing in Rust at this point. Infineon is one, Espressif is another. So kind of talking to Raspberry Pi and pushing them on this point, they said, well, look, we can get you into the beta program. We can give you access to the 2350, before it comes out. Is that interesting? Can you do something with it? So I said, sure, send me the hardware. We'll see what we can do. So I received my RP2350s around Christmas time. And so it's about 9 months before launch, I got on the program. And it's a really interesting chip because it's a lot like the 2040 and then quite different in other ways.
Yes.
One of the significant challenges we have is Raspberry Pi changed the debug interface. And normally debug interfaces are things you don't really have to worry about. There's an ARM standard. You plug in your ARM compatible USB debugger, be it a Raspberry Pi debug probe or a Sega J-Link, or there's any number of USB to ARM debug adapters available. You plug them in, you run the software, and everything's fairly straightforward. Most of the chips on the market use version 5 of ARM's debug interface. I think it's version 5.2. And Raspberry Pi picked up version 6 because why not? I guess they go through ARM's catalog like a shopping list and go, well, we'll have one of those, we'll have one of those, we'll have a couple of UARTs, a couple of timers, and why not use ARM debug interface version 6, especially as they have sort of a dual core setup, which is fine if you use their copy of OpenOCD. But all of the Rust developers like to use the Rust native debug tool, and that's called ProbeRS. And that is a tool that can flash your microcontroller. It can pull out real-time logs without having to set up a UART. It can even sort of execute unit tests. It's really popular, really powerful, and it doesn't support ARM debug interface version 6. And I looked at the ADI version 6 specs, and they're like a couple of thousand pages. And I thought, I don't know enough to be able to do this. So I was able to get the RP2350 running with Rust. I ported all the drivers over, the PIO, everything that worked on 2040 works on 2350, and it was ready to go on launch day. But the caveat was you have to program it with Pico tool. You can't program it with the Rust native tools yet. Some excellent people have done some excellent work, and we have proof of concepts running. The problem we've got is there's a lot of duplication between the version 5 and the version 6 support. And while it works, it's not pretty. So there's just sort of some rationalization required to kind of tidy that all up. And then we'll be able to have kind of sort of almost pure kind of a pure Rust experience on the 2350 using the tools that people are familiar with from programming other chips in Rust.
So, yeah. But you talked a minute ago about, you know, how starting your Rust journey, working on what was just the daily builds of Rust and all of the challenges that had. So that must have been for your own personal projects rather than any client work. What are the sort of projects you work on?
Yeah, back then, it was certainly a challenge to kind of sell Rust professionally. And they're like, well, I'll just use C because I used C last time and C works fine. Fortunately, that's starting to change. Certainly, we're getting a lot more interest from industry going, yeah, no, we recognize actually writing firmware in C is challenging, and maybe there is now a better way to do it. So yeah, personal projects were a great way of just showing off what Rust can do. And one of my early projects back when I was using a Texas Instruments Stellaris, a Cortex-M, that doesn't seem to have been very popular, but they had some low-cost dev kits. So it was a Cortex-M for 32K of RAM, 80 megahertz. And I set myself the challenge, can I get it to generate video? That seems like a hard real-time problem. And if we can do that in Rust, that kind of demonstrates that, yeah, Rust is suitable for kind of hard real-time problems, and all the performance we need is there. And I've got a great selection of photos. I gave a talk at Euro Rust in 2023 on this subject. We started out with sort of just a green vertical line on the screen. I was generating VGA video. I was very lucky that 80 megahertz clock speed happens to be twice the pixel frequency when you're at 800 by 600. So it all kind of worked out quite neatly. But I got a green vertical line, and then I was sort of drawing blocks of color, and then I wrote a text renderer in Rust. So we're sort of converting characters to pixels in real time, which turned out to be super important because that chip only had 32K of RAM, which is not big enough to hold an 800 by 600 frame buffer. It doesn't fit. So instead, you store the characters in memory, and you convert the characters to pixels in real time. And I had loads of fun with that, trying to get color working out of 3 synchronized SPI peripherals that weren't designed to do that at all. And what I'd ended up with was a really great tech demo, really more like a stack of pancakes of tech demos, and they're all built on top of each other. And none of them was really what I would call production grade. And it was around 2020, I thought, I've been at this for 3 years. Now it's probably a time to draw a line under this demo. It's called the Monotron, and you can see examples of it online. We'll draw a line under this, and we'll start again. But this time, let's try and build a computer. Let's not just do a series of tech demos. Let's actually build something like a 1980 style home computer, but using an ARM microcontroller instead of a Z80. I wouldn't mind using a Z80, but if I use a Z80, I can't use Rust. And I really wanted to do it in Rust. So an ARM Cortex-M microcontroller is really, I mean, it's probably still an order of magnitude faster than those sort of 8-bit machines, but it's sort of maybe Amiga kind of performance, perhaps, that kind of spec. So I started on that project. It's called the Neutron. And then when the Raspberry Pi 2040 came out, I immediately ditched my Texas Instruments chip because it was vastly more expensive and vastly less powerful. And the second core turned out to be really useful because on the TI chip, when there's only a single core, that core is spending most of its time drawing the video. And actually, the program only really runs in the vertical blanking interval. which is a genius hack I stole from the Sinclair ZX80 and the ZX81. You know, the CPU can't do any work while the screen's being drawn is, you know, a nice retro aesthetic, but not actually a great computer. So the 2040 giving me 2 processors is brilliant because Core 1 can just draw all of the video in glorious 16 colors. We can use a proper sort of VGA resolution. And then Core 0 can run the operating system. So I've effectively sort of rewritten MS-DOS, but for ARM and in Rust. So we boot up to a prompt, we can do directory listings, we can load programs off disk. I had to write an ELF parser and loader to make that work. I had to write a keyboard driver. You can ask me anything you like about IBM scan code set 1 and set 2, because I've had to dive into that far too deeply. Every single one of the things I added to this operating system turned out to be a rabbit hole you can fall down quite deeply. I wrote an SD card driver in Rust, FAT32 implementation from scratch, SD card protocol, so you can read and write files on disk. And then at RustConf this year, 2024, I gave my sort of a presentation on where I am with the project, and the kind of the culmination of all the work I've done on it is I can boot it to a console. I can load a program I wrote called Neo Tracker. So that gets loaded off disk into RAM and executed. Remember, we're only on an ARM Cortex-M here, so that's kind of unusual to be loading things off disk. Normally, they have to go into flash. And the Neo Tracker is an Amiga 4-channel Pro Tracker player. So it pops up with a lovely sort of ASCII art display on the screen in sort of a classic style. And then I played a 4-channel Amiga Pro Tracker file at the conference. So that's about as far as the system has got. There's always more to be done.
Wow, that's really quite impressive, I must admit. Especially, you know, as a newbie coming to the world of Rust, you know, I got lost day one with trying to understand all of the different HALs that are available for the same chip, and which one I should be using and which direction. I mean, I imagine that's a common issue with people coming to Rust. How do you advise?
So that's an interesting one, because on one hand, you might say, well, that seems like a redundant, that's a duplication of effort. Why are there 2 independent groups producing Rust drivers for the same chip? But on the other hand, why does every chip have to have a single authority in terms of the drivers available for it? We said the manufacturers aren't really paying for any of this, apart from Espressif, who just hired all of the open source developers doing Rust on their chips, and Infineon, who've announced some interest. The Rust for Nordic is done without Nordic Semiconductor's help. The Rust for Raspberry Pi is largely done without their help, you know, barring, you know, early access to hardware. That certainly helps. So yeah, back in 2020, when the chip came out, effectively 2 groups sort of started in parallel working on drivers for the chip. The Embassy group, so Embassy RP, I think is the name of the RP2040 drivers from them. Their focus is asynchronous Rust. That's what Embassy is. It's the embedded asynchronous runtime. And that means their APIs are asynchronous APIs first, but they have non-asynchronous APIs as well. And back in 2020, that was less interesting to me, because asynchronous Rust, certainly on embedded systems, you needed the nightly compiler. And I thought, no, I've been there. I've used the nightly compiler for microcontrollers. I don't want to do that again. I like to stick to stable Rust. So the RPRS folks, who I generally hang out with, we were writing drivers that sort of a synchronous API first. So you want to send 10 bytes to the UART, nothing's going to happen until all 10 bytes have been transmitted, and then the program can continue. And then we're starting to add asynchronous APIs. But they have a different flavor, they have a different style. As to which you should pick, have a look at the examples. Think of a thing that you want to do with your embedded system, because it's always good to have a goal in mind. Have a look at the examples available in the Embassy project, and have a look at the examples available with RPRS, and see which one's got an example that kind of is closest to a good starting point for you. they both work really well. Certainly with the 2350, there's a lot more sort of swapping and passing code between them. So really, it's just a style thing at this point, and either of them is a good place to start.
That's nice. Thank you very much. That helps a lot, and it begins to lean on my other question, because certainly when I look at it and think about it for the audience of my channel and the sort of stuff I build, a lot of that is IoT, and therefore starts to get into all the protocols. And generally, when you start talking about internet protocols, you want some sort of real-time operating system, because you want threads sitting there in the background, looking after those protocols and making sure that things happen at the right amount of time without having to worry about it, or worry about releasing your current main threads so that other things can run. That's generally my sort of feel, and I do the same thing very much when I get into the world of robotics as well, because I tend to build my robot as a bunch of agents that are all talking and then communicating. So therefore, that separation of control is really, really important. Now that sounds a little bit like the async world and therefore Embassy, but not quite, because when I look at async, it sort of suggests that you've got to be quite cooperative in how you multitask, which is not where I think a lot of modern RTOS style interfaces are. Your thoughts?
Yeah, this is a really interesting one. So just to explain briefly what asynchronous Rust does, you mark a function as being asynchronous, and instead of returning the thing that you want, whatever the function is going to produce, it returns a Rust type known as a future. This is very similar to a promise in JavaScript, but it basically says this represents some piece of information that's going to be available later, but it's not available yet. And then you require to poll the future. So keep asking the future, are you nearly done yet? Are you nearly done yet? And eventually it says yes, and it gives you the value you want. And what Embassy does is it provides a thing called an executor, which sits in the background, and it maintains a list of all of the futures that currently exist and just keeps asking them all in turn, are you done yet? And if they are, then things can move forward. The magic the Rust compiler offers is if you write a function that is asynchronous and you've got a bunch of asynchronous operations you want to do within that, maybe, I don't know, open the network connection, read 10 bytes, send 10 bytes, and then close the socket. For each of those, you would await on the result of that asynchronous operation. And what Rust will do is that function, let's call it, I don't know, upload a log message. That function doesn't really exist at the machine code level. Because it's an asynchronous function, the Rust compiler is going to look at it and it's going to divide it up into a state machine, and it's going to write little bits of code that take you from one state to the next. So there's a piece of code that takes you up to opening the connection, and then another piece of code that takes you from connection is now open to now I'm sending 10 bytes, and we need to wait until they've all been sent. So like you, I came from a sort of an RTOS background, and I'm used to the idea of writing my tasks in my system as threads and having them pass messages between them. So I'm used to writing the state machines by hand. I used to have a big Excel-based state machine generator, and you could put the state machine into Excel, and a VB script program would spit out all of the source code to manage the events and transfer you to between states. With asynchronous Rust, the compiler is generating that state machine for you. It is waiting for the event that says, yes, the socket is now open, and it's building a state machine that takes that event and transitions you from one state to the other. And any context you're using, all of the state that needs to be remembered as part of this state machine is all handled automatically, which on the one hand is brilliant, because you can just write a very simple linear looking function, and actually it's going to get broken into 16 different bits of code, and they're all going to get swapped and resumed as and when necessary. And if there's no work to be done, then the processor goes to sleep waiting for an interrupt. So that's very smart. And if you're doing networking in Rust, the Embassy project is probably kind of the area you want to be in, because there's a lot of network protocols and good support for Wi-Fi and things like that. The thing that I've found challenging, and that's kind of a me thing, not an embassy thing. The thing I found challenging is I'm used to writing those state machines by hand. So the idea that the compiler might eat the source code for my function and then actually go and produce 16 different little tiny functions and join them all together with a state machine in the background, it's a different mindset. As I say, I'm used to doing those kind of state machines by hand. So one of the approaches I like on Rust is you can just use a real-time operating system. You could use things like Eclipse ThreadX. You could use Zephyr. You could use FreeRTOS. ThreadX and FreeRTOS are quite nice. You can just compile them as a static library. So pre-compile all the C code, drop that static library into your Rust project, and then you can just call the APIs. So there's some API for start scheduler, then there'll be APIs for spawn, thread, create, message queue, and all of that. You can do all of that from Rust. It's excellent sort of interoperability with existing C code. Zephyr's a bit more challenging because it brings its own build system and its own board support packages, and the Zephyr world is a very Zephyr flavored world. But you can run Rust applications on top of Zephyr. There, it's the Rust application that gets compiled as a static library, and Zephyr deals with everything else. So then you just drop a little bit of Rust into your Zephyr program, and you can write your tasks in Rust. Whereas I say the sort of more classic approach with FreeRTOS and ThreadX, it's the real-time operating system that gets pre-compiled, and a little bit of pre-compiled C is then dropped into your Rust application. But they both work very well, and I have this thing that comes up in training because people keep asking me, oh, how should I do this? And I have this answer that applies to almost any computer science question. And the answer is very simply, it depends. Like, which approach is best for the system you're building? You know, I can't give concrete answers. It depends.
Yeah, you know, the details of design. But it's interesting hearing the different approaches, and it's also interesting hearing that you're actually mixing Rust with those quite good history and good quality sort of RTOS environments is really available, because you're building off the shoulder of giants.
Yeah.
In capability, which I think is sometimes nice and feels a little bit more comfortable than completely changing mindsets.
I know there are some people in the Rust sort of communities who are known for being very enthusiastic, rewrite everything in Rust people. And you know, that's fine. A lot of the good early Rust demos, my demos, came about because I'm like, no, I just want to rewrite it in Rust. I could have used FATFS and the Arduino SD card library. I rewrote it in Rust. But as someone who sells a commercial compiler aimed at sort of business critical and mission critical systems, that's an industry that maybe rewriting everything from scratch is not necessarily the best approach. And so being iterative and being able to deploy on top of kind of the systems you're familiar with makes a lot of sense. And that's why just Rust is really good at that, because it's excellent at calling functions written in C, but it's also excellent at pretending it's a function that was written in C. And so you can make function calls in both directions. And that's one of the things that makes Rust a great systems programming language, that we're still able to have hash maps and vectors and a build system and a package manager and all those kind of nice modern things that you also got in Go and C# and Java. But at the same time, we can make ARM machine code for a Cortex-M. We can be the first thing that runs on startup, and we can play nicely with other machine code that was compiled from C or C++.
So what would be your advice to someone getting started in the world of embedded development with Rust? Where should they start, and how do you get into it?
I think a great place to start is a place called the Awesome Embedded Rust list, which is kind of a curated list of Rust crates for various different bits of hardware. So I don't know about you, but certainly I have a little box of sort of project PCBs that I keep buying and think I'll do something with that. And then that day may or may not come around. Just grab a thing you've got in a box and look at it and go, oh, it's an Adafruit TFT LCD, or it's a Bosch CO2 sensor, or whatever it happens to be. go and have a look at the awesome embedded Rust list and see if someone's already written a driver for it. You can also search on the Rust package repository, crates.io. And if a driver exists for it, then great. You can just start to, wire some stuff up on a breadboard, I2C or SPI, whatever it happens to be. Pick a development board you've got kicking around. You might have ST micronucleo boards, discovery boards. You might have boards from Nordic. The NRF52 is quite popular. Loads of boards, great Rust support. The Raspberry Pi Pico or the Pico 2 would work fine. Drop them in a breadboard, wire it up, and then sort of assemble all the crates. I actually I went down to Bucharest in Romania to see some university students there who were learning embedded Rust as part of their degree. So they're learning embedded systems. They haven't learned C. They've just gone straight into doing embedded systems in Rust. And I went down to judge some of the projects they'd been working on, and they'd basically done exactly that. They'd learned just enough Rust to be dangerous. They'd gone online to the package repository and gone, well, I have one of those screens and there's the driver. So they've downloaded it, they've downloaded this, and they've assembled it together. And not all of them worked, but a lot of them had a lot of great success, some really fascinating projects. So that really is kind of a great way to start. Just kind of grab these excellent resources that are available online, have a look at the awesome embedded Rust page. There's also a couple of books written by the Embedded Devices Working Group, completely free of charge online. So go and look up the Rust Embedded book. That's also a great place to start. Loads of great resources, so there's no excuse.
Brilliant. I will try and find the links and make sure that they're in the description of the video. So thank you very much. Jonathan, it has been an absolute pleasure talking to you. I feel I've learned so much. So that's really, really great. And I'm sure everyone else listening to this has as well. So thank you very much for your time today. It's been an absolute pleasure talking to you.
Yeah, no, it's been wonderful. I really enjoyed it. Thank you.
I really enjoyed chatting to Jonathan and got some amazing insights. I certainly will be putting some of this to use in some of my future Rust projects. Stay tuned to see what I get up to. If you like this video and it helps your learning or projects, then why not drop me a cash tip using that super thanks button below the video. All the other payments are options in the description. Remember, I'm saving these up to get myself to the open source conference in San Francisco next year, and I'd appreciate your help in getting me there, and I hope to see you there too. Thank you very much for watching. If you enjoyed the video, then please hit the like button and please subscribe to my channel so you don't miss the next video. Bye bye for now.